All right, another optimization problem. This time we're given a 20 by 24 inch piece of paper, and we're going to cut the squares out of each corner. Once you do that, that's actually going to create for you a T-shape. As you can see here, if we cut out a square out of each corner, and then you can fold the sides up, fold the flaps up to form a rectangular box, a rectangular solid. Actually, it's not really a solid. What size square we want to determine will give this the most volume. So we begin by labeling the side of the square that we're taking out. Each of those would be x by x. We want to find out which size square would actually lead to the box, the rectangular box, with the most volume. Well, we recall that volume is length times width times height, and here I've redrawn the box. This is what it would look like once we fold it up. We have sides of length x, and then you may want to hold on just for a second there. Where did those other sides come from? Well, when I've taken the x side size square out of the two sides, that side down there with the 20 is no longer 20, it's 20 minus 2x. And same thing with the 24. It's going to be 24 minus 2x. So at this point we have our volume, or we have our box. Now we just need to write its volume. Well, volume is length times width times height. So we would have this expression. And again, just copying that over to give us some more space. We can multiply through. Volume is 480x minus 88x squared plus 4x cubed. Don't forget, before we do our derivative, to find some restrictions. So again, here we can see that we have a 20 minus 2x. If we make x too big, that side will not be a side. Likewise, we need to actually cut a rectangle out, otherwise we don't have a box. Putting those two ideas together, we get our x's between 0 and 10. X is between 0 and 10. Because if it's any bigger than 10, then that 20 minus 2x is not actually going to be a side. So now we have our restrictions. We can take our derivative. Now our derivative, we look for when it's 0 or undefined. The derivative in this case is a polynomial, so it will never be undefined, so we're really just worried about it being 0. So at this point we can solve that equation. Now we can actually divide everything by 4, and then I'm just going to rearrange things. That gives me the equation 3x squared minus 44x plus 120 equals 0. And now we can solve that equation by using the quadratic formula. You may want to pause and go ahead and do that. I went ahead now and actually solved that and got two answers. X is 3.62 and x is 11.05. But here's where our restrictions become important. 11.05 is bigger than 10. So if we cut an 11.05 square out of each corner, we're not even going to have any, we're not going to have, we're just going to actually have a little strip of paper left over. So that won't work. So we can throw that away because it's too big. And so then we look at our 3.62 as hopefully being the one that will lead to a maximum value. But we should first test the derivative for values above and below 3.62 to see that the volume is increasing before we get to 3.62 and it is decreasing afterwards. Okay, now at this point we can say, okay, that is our max. And so we can say that we need to cut out a 3.62 by 3.62 square. So if you look at the graph of V, that's what I've actually drawn over here, we can see that we have a maximum value, again occurring at roughly 3.62. That will lead to the maximum volume. Okay, so hopefully as you're doing these optimization problems, these examples are kind of getting you some little insight and helping you develop a little bit of intuition about how you need to solve these problems. Until next time.